Okay, so welcome back to this next lecture. And now we want to talk about harmonic analysis or Fourier analysis in the group ZP. And you will now see that basically we just use the same kind of definitions that you might have seen maybe in the previous years or somewhere in the real line. But then all the theorems and everything will be really the same. And we won't have these issues of something called measurability issues that you might have in the more abstract method theory classes or Fourier analysis classes, but instead we will see the basic ideas that we can do in this notion. So let's define the Fourier transform. So let's start Fourier in ZP. So what we have here is this definition of Fourier transform. So let's call it the Fourier transform of a function f. Let's call it any function from ZP, and let's make it complex valued function. Any function of ZP in the frequency k, which is actually a point in ZP. So that's an important distinction. So it's only that these points in ZP is the complex number f hat k, and we define it to be just this summation t of ZP, and then f of t and e to the power minus 2 pi I k t over p. So we have this kind of a division over p to make it somehow normal. We will see later that this helps with the kind of theoretical considerations. And so basically what we see here is this notion like basically a sum of complex numbers. So these numbers here, what we have here, so this could be considered as on the circle. So this is the complex plane over here, and now we have the unit circle here. Let's say we have this unit circle here. So this is the unit circle. Unit circle in C, then these numbers are in the unit circle. Let's call it the unit circle S1, for example, S1. I think this is an also sometimes is used. So all these like basically are numbers and complex numbers over here that we are adding together. So this could be really, they are not like in the ZP that they are like basically equidistributed on the circle, but they can be anywhere in the plane. So this is really a big difference that these numbers, when you change the possible numbers of different t's, it depends on what k you use, for example, and it becomes more like the number theoretic properties of these numbers. We see like various different numbers that you could find inside this circle. So that's are the numbers that you're adding together, and then you have weights on them. So each of them has maybe a weight. So that's the kind of weight that we have here. And then that's way we can compute the Fourier transforms. So different like arrows that you're adding together. Let's say this would be a number, and then it would be a number. These are the weights. And at different weights. So that's the putting like what direction you're adding them, and then hopefully you get this kind of you get some kind of a complex number in the end. So this looks a bit of a messy kind of a situation, but then actually it captures a lot of information about the function itself. So let me like do two examples which are quite important. So first of all, we have this kind of lemma that allows you to do a lot of computations in here, which is basically something called exponential sum formula. which is the following, that if theta is not 0, then the sum of t from 0 to p minus 1 of e I t theta is equal to 1 minus e to the power I p theta, 1 minus e to the power I theta. So this is a lemma basically that we will be using a lot in this course. But this is, if you think about what is gives this lemma, this is a basic thing about geometric progressions. We just basically, you can see that here basically proof is like the proof of sums of geometric progressions. So if you remember geometric progressions, you're basically summing over powers of these numbers. And here we are summing from 0 to p minus 1 of powers of complex numbers. So these are powers of complex numbers, but you have the same type of like a proof that when you add the kind of numbers together, you can get this kind of formula with this expression. But then using this lemma, you can do a lot of like examples of computing Fourier transform. So let's go take some examples. So let's take this, maybe example 1 is the uniform distribution. So remember, lambda t is 1 over p as t is in zp. Then we can compute the Fourier transform at k. So by definition, this is just given by the sum t in zp of lambda t e to the power minus 2 pi I k t over p. That's the definition. And now we can open this up. So this is 1 over p. So we obtain t in, well, actually we can make this into a sum from 0 to p minus 1, 1 over p e to the power minus 2 pi I k t over p. Take the 1 over p in the front, and it becomes p minus 1 of e to the power minus 2 pi I k t over p. And if you set theta now to be equal to minus 2 pi k t over p, that's the number we want to put. And if theta is not equal to 0, we can just compute this sum, that this is equal to 1 over p, and then using this exponential sum formula with this theta, it becomes 1 minus e to the power, ip theta over 1 minus e to the power I theta. So that's the kind of exponential sum formula that use it with this specific theta. So if you assume that theta is not equal to 0, so just in this case, when we obtain this type of a formula on this expression. But then if you actually open this up, this is 1 over p, 1 minus e to the power, this is 2 pi I k, ki actually, and then 1 minus, because that's the p divided, multiplied by that. There's actually a minus here, and then e to the power minus 2 pi I k over p. Then what you actually have obtained, that this number here, this 1 minus this is actually 0. Because the complex number, so e to the power minus 2 pi I k, so if you think about this as in the complex plane, you're basically taking this back to being number 1. So this is the complex number 1 over here, and then with the argument being equal to 2 pi integer multiple of k, you will always get this. Remember that k is zp, so k is an integer in particular. So this means that this whole thing is 0 when this theta is equal to non-zero, which means that when minus 2 pi k over p is equal to non-zero, which means that if k is equal to non-zero. So we have just proved that Fourier transform of k is equal to 0 when k is equal to non-zero. So that's quite an interesting property for the uniform distribution, that you have basically able to prove that the Fourier transform is 0 when k is equal to non-zero. But then using this property as well, what about k is equal to 0? Well, then you can just use the computation. So Fourier transform 0, this is sum t from zb of lambda t e to the power minus 2 pi I 0 t over p, but that's just 0, so this just becomes 1 for every point if you want to consider, and then this is equal to 1 over p. So then this whole thing is just t in zp of 1 over p, which is 1. So we have just proven that the lambda Fourier transform k is equal to 1 and 0, and this is when when the k is equal to 0 and k is not equal to 0, which is kind of like an interesting property. But then at the same time, like, what about happens to the other extreme? So when we have the Dirac mass. So let's take another example. Let's put the Dirac mass S t, which remember was 1, 0 when t is equal to s and t is not equal to s in point in zp and t is equal to zp. So that's first the Dirac mass. Then the Fourier transform, if you compute this at k, is then if we compute this number again by the definition, this is the sum over zp Dirac st e to the power minus 2 pi I k t over p. And now you can see that this quantity here, by definition, is only 1. It's actually non-zero only when t is equal to s. So what you just obtain is that the only thing that remains is minus 2 pi I s over p. So that's the Fourier transform for any k in zp. So no matter what k we choose, we get the same quantity. Sorry, this would be k s over p. Yeah. So thus, in particular, we'd have that if you take the absolute value of delta s Fourier transform of k, which is then the absolute value of this minus 2 pi I k s over p, then this is equal to 1 for every k in zp. And if you want to compute the k equals 0 case, we just have the same way, k equals 0 by using the computation. If you put it actually in this case equal to 0, it's just equal to 1 as well. So that's the kind of thing. So what we have basically obtained is that the Dirac mass has this nice property that the Fourier transform of the Dirac mass at s at k is just has this interesting ik s over p formula. Well, you could just put this back here. Oh, sorry. And why is this like useful now is that what we have seen is that this is actually, when k is not equal to 0, we can see that it has absolute value 1. So let's, if we take this, I can write this as this is equal to 1 for any k in zp. But note that if we take the Lebesgue measure and take its Fourier transform, then this is equal to actually 0 for any k not equal to 0. So there's like a big difference between this kind of very concentrated distribution of the Dirac mass and then the very uniform distribution, that when you take the Fourier transform of these things, the roles are reversed. So instead of starting from the distribution, let's say we started from the Lebesgue distribution that is very uniform, like this is like our Z4 and this is our lambda, and then you would have maybe the possibility of the Dirac distribution where you would have maybe everything in one, so that Dirac S and this is lambda. Then when you take the Fourier transform, so lambda bar or lambda bar and Dirac S bar, then you end up into a situation you could actually think about the numbers that you obtain in the complex plane. You could put them into a unit circle. Let's say we put them onto a unit circle, and the same way here. Everything is now concentrated on the position 0, so there's basically a Dirac mass at 0. Maybe move that a bit. And then in the other case, so this is our lambda bar, we are basically uniformly distributed. So in some sense, we have this uniform distribution here. So we have the weight 1 at every point. In some sense, this is a complex number, so it's not exactly the same situation. So it's a complex valued object, but it kind of concentrates on those points in this way. So it is actually kind of goes into in an absolute value that is given by that. So that's what you can think, that there's this kind of dichotomy, and that means that when you want to actually study, for example, how uniform some general measure, for example, is, then in the Fourier space you need to study how concentrated is the distribution. So that sometimes can be easier, actually, that when you start from, let's say, I don't know, we could, for example, take this, maybe example 3, take the mu is equal to a half Dirac minus 1 plus half Dirac 1, which we've been using, and take this, for example, in ZP. And now we can obtain that the Fourier transform of this, if you compute this, we can just actually use the definition again, t in ZP, mu t e to the power minus 2 pi I kt over p. Then, because it's only at 2 points is equal to a half, we actually get this is equal to a half on those weights e to the power minus 2 pi I k, and that's at the point 1, so it's over p, and then half e to the power plus 2 pi I k over p. We could write this in this form for the Fourier transform. And then actually there is a formula in complex analysis that if you have like basically an average of these type of complex numbers, this is actually the same as cosine of 2 pi k over p at that frequency that we have taken. So now you can see that this complex number is somehow in between. So different on different values of k, you might have different like very small values or large values. So what we can see basically is that, as I said, if you take the uniform distribution and then you take the mu and then you take the Dirac mass at the point, we remember that this was like very uniform distribution. Then this one is basically maybe at some points it gets more values, and then other points it gets like larger values. You could say maybe write this as like this, like a uniform distribution, and the Dirac mass was just basically concentrated on these points. So there is like the Fourier transform of this mu is somewhere in between the Fourier transform of the Dirac mass and the Fourier transform to uniform distribution. And you can see that you can compute it from the numbers of this cosine, what you get in this situation. So there are many examples we could try to compute in the same way. And basically, in the future, we will see that when you study the random walk, by understanding this number, just the Fourier transform itself of the driving probability distribution, we can do most of the analysis already. Like, for example, when we want to study the mixing of the random walk, we can just reduce it basically to understanding the Fourier transforms in this way. So I hope you got something out of this idea, and in the next lecture I plan to go into this idea of Fourier series and the inverse Fourier transform, which allows you to connect the Fourier transforms back to the original function, a bit like we have done maybe if you have done some other courses in the past, or maybe seen this before in the real line, you could do. Okay, that's all. Thanks.